Hello and welcome to the series of lectures on operating system course. In today's lecture, we learn about process synchronization. So processes, as we know, can execute concurrently. So concurrently means in an interleaved time fashion. Okay, so it can be interpreted at any time, partially completing the execution. Concurrent processes Concurrent access to shared data may result in data inconsistency. That is, two or more processes sharing a common data and while executing in a interleaved time manner or concurrent manner. So there is a chance that one process may get inconsistent data while processing. So that concurrent access to shared data is very important and it may result in data inconsistency. So maintaining data consistency requires mechanisms to ensure the orderly execution of cooperating processes. Right? Suppose that we want to provide a solution to the consumer producer problem that fills all the buffers. Already we learned in the unit 1. So we can do so having an integer counter that keeps track of the number of full buffers. Initially the counter is set to 0. Whenever it is producer produces an item, the counter is incremented, and whenever the consumer consumes an item, the corresponding counter is decremented in the consumer process. So the typical pseudocode for the producer problem is here. So when the counter is equal to buffer size, then the producer cannot produce an item because already the buffer is full. And if it is not the case, it will come out of this while loop, and the corresponding the location pointed by the in pointer, the new item will be produced, and the in pointer will be incremented to the next available space in the buffer, and the counter is incremented. In the case of consumer process, if the counter is equal to 0, then it is considered as the buffer is empty, there is no item to consume. If it is not the case, the corresponding location pointed by the out pointer, the corresponding item will be consumed. Then the out pointer will be incremented to the next available position and the counter value will be decremented. So this counter is a variable, okay, which is used for corresponding problem. What is that? In the earlier case, without the counter implementation, we could store only n-1 items in the buffer. But when we add a counter variable that is shared by both the producer and the consumer process, okay, we can utilize the buffer to the fullest. So if there is a buffer is 10 size of 10, all the 10 locations can be accommodated in this case of implementation. Right now, because this counter variable is shared by the producer and consumer, there is a chance of race condition during the interleaved execution of this producer and consumer problem that we are going to in the next slide. So what is this race condition? Actually, when at the hardware level, this counter plus plus, there is a post increment operator and post decrement operator which we are used, it can be implemented in the 3 different instructions. What is the 3 different instructions? The counter variable value, the latest value of counter should be assigned to a register. Then the register value is incremented to 1. So the corresponding updated value is again assigned to the counter. So single counter plus plus post increment operation or single counter minus minus post decrement operation is actually implemented in 3 different instructions. So when we consider the interleaved execution of both the producer and consumer process, which shares this counter variable, so what will happen? For example, during the count sequence, if we consider count is equal to 5 initially, and if the producer executes register is equal to counter, that is register 1 is equal to counter, register 1 will be having value 5 because the counter value we consider it as 5. Now the second time at CS1, producer executes register 1 equal to register 1 plus 1 and the register 1 is incremented to 6. Before the execution of counter is equal to register 1, what happens at time S2? The consumer process executes the register 2 equal to counter, and what will happen? Whatever the value of register counter value currently, it is 5, still 5. It is not updated to 6. Because the last statement is not executed, right? At time S2, still the counter value is 5. So the counter value 5 will be assigned to register 2 at time S2, and time S3 again the consumer process executes, in which it decrements the register value of 2. So the register 2 value is 5, 5 minus 1 is equal to 4. Now at time S4, the producer executes the last statement of counter equal to register 1. Now the value will be 6, and consumer executes the last statement counter equal to register 2. Now the value will be 4. But eventually the correct value is 5, because one time the producer executes, the counter is incremented. So from 5 to 5, it should be increased to 6. When the next consumer executes, it is decremented to 1. So 6 minus 1 is again 5. But both the value of 6 and 4 is incorrect. So this we say it as a race condition, and here the shared variable counter has inconsistent data in the cases of during the course of execution. So this problem we need to avoid. So whenever processes shares a common data, okay, that instructions pertaining to accessing of common data, we call it as a critical section. So considering a system of n processes, each process has critical section segment of code. In that particular code, they may change the common variables, updating the values, writing the files. So when one process in its critical section, no other process should be allowed to enter the critical section, because it will provide the inconsistent data. So the critical section problem should be solved. So each process must ask a permission to enter the critical section in the entry section, and may follow the critical section with the exit section and then the remainder section. So there will be a sequence of a scheme of execution. Whenever a process wishing to enter the critical section, it should execute the entry section. Then after entry section, it should execute the critical section, and then it should execute the exit section, followed by the remainder section. So this sequence of action should be performed. Now for algorithm for process P suffix I, for solving this critical section problem, we will consider a simple example with a variable turn. Whatever the turn means whichever process is ready to enter the critical section. So that will be assigned to turn. So while turn equal to j, for example, if process Pi is willing to enter the critical section, it checks whether turn equal to j. If turn equal to j means j is ready to enter the critical section. So if j is ready to enter the critical section, process Pi should wait. So if you see the semicolon here, so if turn equal to j is true, Pi waits. Okay, if turn is not equal to j, then Pi enters the critical section and assigns the turn value to j. So what it means? So Pi says that I have entered the critical section. Now Pj can enter the critical section. Okay, so this is a simple solution. But when providing a solution to the critical section problem, 3 more requirements are needed. Very important 3 requirements. What is that? A mutual exclusion should be preserved, progress requirement should be preserved, and bounded waiting should be preserved. So what is mutual exclusion? If process Pi is executing in its critical section, then no other processes can be executing in their critical sections. That is called as mutual exclusion. Progress. If no process is executing in its critical section and there exist some processes that wish to enter their critical section, then the selection of processes that will enter the critical section next cannot be postponed indefinitely. We should not postpone the selection of processes waiting to enter the critical section. That is called as progress. Bounded waiting. A bound must exist on the number of times that processes are allowed to enter the critical section after a process has made a request to enter its critical section and before that request is granted. So these 3 requirements must be satisfied. And 2 approaches, depending on if kernel is preemptive or non-preemptive, there is a preemptive, non-preemptive way of handling the critical section in operating system. In preemptive, the allows preemption of processes running in kernel mode. Non-preemptive runs until exits the kernel mode blocks or voluntarily yields the CPU. Right. Now we will go for a typical solution of a 2-process solution. Actually, in practical, there are n number of processes available. The n number of processes can share data. But to start with, we will consider a solution for 2-process solution, considering only there are 2 processes. This simple solution is provided by Petersons. That is why it is called as Petersons solution. And this is a software-based solution. It is a simple algorithmic approach for 2-process critical section problem. So we are going to assume that load and store machine language instructions are atomic. So what is meant to be atomic? Atomic means the set of instructions should be executed without interruption. That is called as atomic. Okay, so that cannot be interrupted. Here in this Petersons solutions, we will have two variables, two shared variables. One is called as integer variable, that is turn. Another one is Boolean flag. Okay, flag is a Boolean variable. What is the functionality of variable turn? What it signifies? The variable turn indicates whose turn is to enter the critical section. The flag array is used to indicate if a process is ready to enter the critical section. If the flag of I is equal to true means implies that process Pi is ready. Now this is the pseudocode for algorithm specified for process Pi. For example, if process Pi is ready to enter the critical section, then flag of I is equal to true. Immediately what happens, it assigns the turn value to j, okay, so that if j wants to enter the critical section, it may do so, okay, before Pi enters the critical section, it executes this entry section. What is that specified in the entry section? It checks whether the flag of j is true. Flag of j is true means j is ready for executing the critical section, and turn is equal to j. If both are true, Pi cannot enter the critical section, it should wait. If any one of these is false, Pi can enter the critical section, and what happens, see, after completing in the exit section, it turns the flag of I is equal to false. So flag of I is equal to false means it has already entered the critical section and now it is not ready for executing the critical section. Thereby, with this thing, whether the mutual exclusion, progress and bounded waiting is considered, is implemented. Yes, mutual exclusion is preserved. How? Pi enters critical section only either flag of j is equal to false or turn equal to I. Otherwise it does not. Progress requirement is also satisfied. How? Because it gives the turn, it makes the flag of I equal to false when it is completed the accessing of critical section, and it gives turns to the next process. Bounded waiting requirement is also met because one time the corresponding Pi has entered the critical section, it gives the next turn to Pj. Similarly, Pj after entering the critical section for one time, it gives the turn to Pi. So in this way, this simple software based solution gives the solution for critical section problem. So in further classes, we will learn about various other process synchronization tool which will solve the critical section problem. Thank you.